Hey everyone, want to welcome you to the latest episode of Math for the Impatient. We have a little special mini series happening. We're here with Stan Kladko, CTO of SKALE, and today we're going to start a 5-part mini series that let's call ZK for the Impatient, where we'll go through and try and give you a little bit more information, a little bit more explanation about what ZK is. I think a lot of people hear the term ZK. It's definitely popular. A lot of people have heard Vitalik talk about it, but a lot of people aren't really sure exactly what ZK is. So Stan, I'm going to throw it over to you. Go through and maybe give us some good analogies around what ZK is in this very first installment. And if you come back, we'll have 4 more installments and we'll get into a little bit more depth each time that we do it. So take it away, Stan.
Yeah, I mean, it's really like a mysterious term because I've heard from many people that, ZK is like a moon math. I don't know what moon math is, but people think it's like, wow, this is something magic or like incomprehensible. And so it's really the case. So the actual purpose of this series for this installments is to kind of demystify it and explain it to people that just know elementary mathematics, like just your school mathematics. And maybe sometime you'll be at a blockchain conference drinking wine with someone or beer or whatever you choose to drink. And this is kind of a nice thing to explain to people, especially if you make things simple. So we really tried to make things really simple, so it's accessible. But before I start, and I'm gonna start with like analogy. I'm going to give you a feeling how things work. So the first installment about just getting the feeling and getting the principles. And then during the next installments, we're going to go in detail. But before we go into this kind of the first thing, let's just talk a little bit, just the 3 things about ZK, which are really fundamental and you need to know. First thing, which is really interesting, is that ZK is kind of a historic term. Maybe that's why people think it's moon math, because it's incomprehensible, right? So there has been this explosion of mathematics starting approximately from the year 2010 about something which is called provable computation, meaning that someone computes something, someone else checks this. So it doesn't really have to do much with zero knowledge. There's a feature inside of it which is called zero knowledge, which is not actually used much for things like rollups or blockchain. But historically, it's called zero ZK. People call it ZK, and we call it ZK, right? I will call it ZK. But every time you hear ZK, just think in your head provable computation, and it actually will make things simpler for you. So then ZK, it's really, the idea is pretty simple. You have a pretty slow computer, and obviously, for us, slow computer means slow and expensive Ethereum mainnet. So you have this slow computer, and the computer doesn't compute things, but then there's a supercomputer which computes really, really, really complex parallel whatever things, which may take days to compute. And then the supercomputer presents things to the slow computer, and the slow computer is able to verify the result. And definitely many examples in the real life about things like that. IRS is a good example. It's really hard to compute taxes. The result is a real single number, how much you pay, basically. And the IRS needs to verify this computation. And it's obvious that IRS is slow, but also other, similar agencies are usually pretty slow. So that's a good example. But for us, it's more important to have a different example, which is Ethereum mainnet versus Scale. Ethereum mainnet, very expensive, very slow. Scale chains are super fast, many of them. But what we want to do, we want to submit a proof of each and every computation that Scale makes, each and every computation. That's super important. And present a proof of it to Ethereum. So then if later every single node in our network is hacked, no one is able to forge things, because if a wrong thing is presented to Ethereum mainnet, Ethereum will be able to find this out. So that's incredibly interesting. And it seems to be even impossible to do, like magic. I think that's why people think ZK is magic. But what we're going to do now, we're going to go into a toy example, which will give you a feeling that it's actually not magic. You actually can verify really, really complex computation on a simple, by a human, essentially, using a very simple technique. And then if you get this feeling, you understand that ZK is possible, and then the rest of the installments are just going to be about better mathematics, how make things better, but the principles are going to be the same. So it's super important for you to understand this first installment, because this is kind of the foundation of everything. So without the further ado, let's go into it. Okay, here's the example. Sorry. Here's the example. Here's the story. The king and the treasurer. And kings, you know, kings, you like to buy things, many things, expensive things. So let's say at the end of the year, the king wants to find out how much money he spent, right? And obviously, because the king suspects that maybe the treasurer is stealing money, so the king wants to know. So there's a list, the actual list is probably like thousands of luxurious items, and this is just a tiny example. So the king bought like a sheep, bananas, a sword, a ring for the queen, you know, the dress, the suit probably, a horse, and a wine. And each and every item has a different price. You see that, you know, the prices crazily fluctuate. And obviously, the ring is the most expensive thing for the kingdom, but other things may also be expensive. So the king has all this list, but the king doesn't want to do this computation. The treasurer is supposed to do it. The king just wants to know the total, right? So what the king does is basically tells to the treasurer, okay, here's the thing, here's the list. So compute the result, but also provide me not just the result, but something which lay people call subtotal, but it's actually a super important term. ZK calls it a trace. You probably heard this as subtotal. Basically, how you add up things, you add up the first thing, the second thing, the third thing, and every time you record the result. So you get the subtotal column. Obviously, at the end of the subtotal column, the very bottom line is the total, right? So the treasurer is supposed to fill out the column and bring back the results to the king. The treasurer goes away, you know, spends weeks adding up the thousands of items and comes back with this table. But then there's a problem, right? The king, how does the king know that the treasurer does not lie, right? It's super important for the king. And this is actually something which is essentially in ancient times. It's a very real example of this happening, right? So the kings always suspected the treasurer, right? So how does the king verify that the treasurer is correct? Well, the technique that everyone uses since the beginning of human civilization, and guys like IRS use it all the time. The technique is called sampling. Basically, the king doesn't have time to compute every single line, but he can randomly choose like 3 lines, 2 lines, and recompute. And if the king finds an error, the treasurer is probably beheaded. But if there's no error, the king will probably say, okay, you know, it does look okay. And actually, IRS pretty much does the same thing. They also always, you know, this one of the techniques they always employ is sampling, right? But sampling has this huge problem. It's really not very secure. And here's a very simple example. It's easy to understand. So let's say, you know, that the king checks these 2 lines, the sword and the horse. What the treasurer can do then is just hacks the thing by modifying the line that the king didn't check. And in this particular example, the treasurer takes the ring and literally writes 1 single digit 1 in front of the price of the ring, which makes the final result like 3 times more. Essentially, by just writing 1 letter, the total changes 3 times. And that's the fragility. You see this very important point about the fragility of mathematics, of computation. If you have very low computation, you can modify a tiny step to totally change the result. That's the fragility of it. And because of the fragility, sampling by itself is not really secure. It's an interesting idea, but it has to be supplanted by something, because by itself, it's really not secure. So then how do you secure sampling, basically? How you tweak things to make them more secure? And that's pretty much the idea of ZK or provable computation. And that's something that really, if you have like the elevator pitch and someone in the elevator asks you, what is ZK? And you just need to say two words. Tell them hidden law. Hidden law. That's the simplest way to explain ZK. So how do you? So the king needs to embed something hidden into these numbers, because the king can always modify like cents in the prices. For the king, it doesn't really matter, how many cents. So the king can tweak the numbers, the part which is cents, really, really easily. But how does the king actually do it? How does the king introduce this hidden law? So here's the example that I did just before a couple of hours before this recording. I did this hidden law thing and modified the table. So the prices just changed a little bit. The difference is tiny, just in cents compared to the previous table we had. So I wonder, Marcus, let me just torture you a little bit. Do you see any hidden law in this numbers? Just take your time. Is there anything suspicious in the numbers?
Yeah, other than that, I knew the other numbers were different. I can't, there's no discernible thing that I can just think of off the top of my head.
Yeah, it's a torture question, because people usually torture people with questions they can't answer, right? If someone would show me, if someone would show me this column, right? It does look legit, right? Like, there's not so much of a difference.
Yeah.
It turns out that actually there is this hidden law, and I don't want to torture you too much and our viewers. It was actually very simple. What I did, I just tweaked the cents. So each of these numbers, if you take them in cents, it's divisible by 13. I mean, it's your homework if you want to verify. For instance, you can take the second line, $7.67. It's 767 cents. Just verify it's divisible by 13. And so there's this hidden order that every single line is divisible, price is divisible by 13. But then there's an incredibly important principle. If you add two numbers divisible by 13, the result is divisible by 13. And if you multiply two numbers divisible by 13, the result will be divisible by 13. Actually only the one of those numbers, so the multiplication needs to be divisible. That's kind of elementary math that you kind of tried when it's your math teacher in elementary school, and you can think about this. But these two things are incredibly important. If you introduce this hidden law that the price is divisible by 13, if you multiply things or add them, the hidden law is preserved. And this is something that in ZK terminology people call gates. They call every multiplication and every addition a gate. This because ZK borrowed terminology from hardware, from chips. And for chips, everything is semiconductors, it's gate. So ZK calls multiplication a gate, additional a gate. And for ZK, exactly this principle is the cornerstone, the foundation of ZK. The ZK uses a hidden law, which is preserved by multiplication and also preserved by addition. So that's the real ZK, not just this toy thing that we're discussing. But let's come back to the toy thing. So every price is divisible by 13, and then the total is 68321.89. You can check on the left. We checked, and it's actually divisible on 13. You divide by 13, you get like an even number of cents. And so the way the king verifies this hidden law is essentially by dividing things by 13. So when things are divided by 13, the king knows that the things are correct.
It says that, is that because 13 is a prime number?
Well, that's a good question. Coming back to ancient Greek, they had this huge idea about numbers being gods, essentially. And they, in particular, they invented prime numbers, right? Greeks. And they also were really obsessed with prime numbers. And why? Well, it turns out that prime numbers are really kind of weird. So things divisible by prime numbers, they actually look much more random. There's kind of randomness in prime numbers, and we're going to actually discuss this principle of randomness of prime numbers during our next installments. But prime numbers like weird, right? 3, 5, 7, 11, 13, all these weird things. So if you think about this, you know, Marcus, if instead of 13, I would take like not a prime number, like 6 or 10. Things would you probably would be able to discern this order. You probably have this feeling that the order would be easier discerned, and we're gonna discuss in detail. But to hide things, for things to look hard to guess, hard to extract this hidden law. Turns out that prime numbers are going to, actually working better, and actually the entire cryptography is actually based on prime numbers. And one of our installments, we're going to talk about the randomness, why prime numbers are more random. And in this particular example, randomness actually hide things better, because these prices look random, right? They don't really look like manipulated, right? But that's a really great question, because we're going to actually cover it in detail in one of our sessions. Now, let me go further. Now, how does the king catch this thief? Let's just take the example we just discussed a couple of minutes ago. The thief, the treasurer, doesn't know anything. And so the treasurer does that thing, adds this digit 1 in front of the ring price. And then magically you see that now the king tries to verify, the total becomes almost 3 times more. But then the king tries to verify, tries to divide, and the division does not have the even number of cents. So the treasury is beheaded. That's it. So that's really, you know, that's really, you know, the moon math. That's the elevator extract of the moon math. But obviously, this example that I brought is good for humans, but not good for computers, because the treasurer probably could guess. The king probably could counteract the treasurer by taking a larger number, like instead of like 13, taking like 23. So the king can counteract, and essentially the entire like explosion of mathematical papers since 2010 is about how to improve things. And the real thing has the same principles, but is not only secure for humans, but also secure for computers. But the essence, the principles are the same. So let me reiterate again what the principles are. And because it is incredible for you to understand the principles for our next sessions, because the next sections are going to be just explaining, going deeper. So this is 3 things: the principle of sampling, the principle of hidden law, and we used this divisibility by 13. It was like a toy example, something that modern mathematicians called modular arithmetics, which is a huge part of number theory. It's actually part of like things like the Fermat theorem, that the proof of Fermat theorem, all of these things are incredibly developed. And the other thing is saying that these things used to be like really toys, you know, interesting parts of mathematics that really didn't have any use, except for people like Greek just, you know, being obsessed about the numbers. But now suddenly you see that the things which are totally abstract suddenly find this very, very practical use of how do you verify scale chains against Ethereum. It's a commercial commercial success of Greeks, like several thousand years after Greeks. So yeah, so that's really, so basically, again, coming back to the elevator pitch, someone asks you what ZK is, tell them that ZK is not actually ZK, it's probable mathematics, probable algorithm. And the three principles: sampling, hidden law, and divisibility. And improving each of them, we can actually design things which can be verified and secure on a computer. So that's it for this session. I hope you now have a little bit of a feeling that it's not really moon math. And the next sessions are gonna go a little deeper. As I mentioned, one of the reasons why people call ZK a moon math, it's several things, so it's not a single thing. And we're gonna go over them in detail, but each of those things can be understood by someone who graduated from a high school in mathematics and doesn't use any like integrals or any complex things, just uses integer numbers. And I hope that we can have more people joining next time to go a little deeper into ZK and also into how we're gonna use ZK to get to the next level with Scale in the year of 2023.
Very cool. So to recap, this was a very quick kind of analogy to understand ZK. There are more coming. So this is part of our ZK for the Impatient series, which is a mini series within the Math for Impatient. Please look below. You can join our Telegram, join our Discord, check us out on Twitter @Scale Network. Thanks, Dan. Appreciate it. Till next time.
Bye, Marcus. Bye, guys.